Okay, on to this example. So we'll use the transadmittance and get this, and then we'll get the gain, V2 over V1. We'll see how these two are connected in a minute. So you can use any valid technique. The slide's going to use Thevenin's. And the first point to note is the VOC between this point and this point without the R, VOC without this R2. It's just going to be this impedance divided by the sum of these two, which you have, excuse me, that's right here, times the V1. So that's not too bad. ZTH, you can short V1 and look at the impedance between this terminal and this terminal, not including R2 again, to get ZTH, which is just this in series with the parallel combination of this and this, which is what this expresses. So you can rewrite it like so, and you can get the least common denominator, which would give you an SL plus R1. So SL R1 times 1 is this. SC times SL R1 gives us S squared L R1, which is this times this. So that's pretty easy to see. Now we have a new circuit as given below here. And we can get I2 is just going to be VOC divided by the sum of the impedances. Now, big complicated equation, like so. Okay, and we multiply both sides by, or excuse me, we multiply the top and bottom by SC, the quantity SL plus R1. Okay, so let's see how that works out. So we should have SC times SL plus R1 will cancel out this factor in the bottom. So we should have all the stuff on the top. S squared LC R1. Where is that? S squared LC R1. There it is. SL. There it is, right there. And R1, all by its lonesome. Good. And the rest of this is R2 times this stuff. So S squared LC R2. There it is, right there. SC R1 R2. There it is, right there. Okay, so we know the bottom's correct. And SL R1 cancels out this SL R1. So we're just going to have S squared LC up top. Transadmittance. That's equal to the current 2 over the voltage input, voltage 1. Which is why V1 doesn't show up. This V1 here doesn't show up down here. So we're convinced of the equation's correctness. And here's the gain, voltage gain, which Vs is going to equal I2 times R2. Well, gee, we've already found I2 over V1 right here. So we can write it like so. So we have an expression for the transadmittance. And then an expression for the gain, voltage gain, GV. So that's just an example of how to go about it. Poles and zeros. So more definitions, more nomenclature, as I call it, more definitions, stuff like that. We noted earlier that you have a transfer function. It can be written as the ratio of polynomials. I even wrote a new octave routine to calculate it. You can find the roots of this polynomial. They might be complex roots, but we're dealing with complex numbers. So you can write that polynomial as the product of s minus all of its roots, and so forth. And then this is just a constant factor right here. Okay, so that constant factor, by the way, would be the AM over BN, because you'll notice the leading term is going to be S to the mth, and the leading term here is going to be S to the nth. So that tells you what K naught is. We know how to compute the gain. If we know the poles and roots, we can compute the gain. So here's an example, and you'll notice the poles in this case are complex, and we're told h at 0 equals 1. So we can write the transfer function s minus z1, which gives us this, and then s minus p1 and s minus p2. We can expand the binomials. These are the ratio of the polynomials you guys are used to. Then we have a K naught. We're told that 0, when s is 0, K naught is 1. So that's K naught has to equal 8. Okay. So find the driving point impedance of this, and that is the impedance, the same node, that is, when voltage and current are measured at the same node. So here's IS, the yes, KVL on the input. We get this stuff here. This is just the impedance of the resistor, impedance of the capacitor. The input impedance, the total input impedance, and putting in numerical values. These numerical values here. So I had to convince myself before I moved on that they're writing down the right stuff. Pi times 10 to the 8th over S, by the way, is 100 times a mega ohm times pi over S. Okay, that's the input impedance. So poles and zeros, and K naught for this expression. It looks like the same circuit as before. I didn't double check that. So we got to get the V out. We write the gain is what we had in the previous example. I just wanted to check. This is the previous slide, slide 14, and this expression for gain was copied over to slide 19 here. Same expression. Now we want to find the poles and zeros. Well, the zeros are going to be 0 in the case of S. There, the gain expression. So 0. Oops, I want to put my pen on. 0. It's the only one, the only 0 on the top. The poles are when this equals well, anyway, S equals negative 100 pi, pole 1, negative 100 pi, and negative 40,000 pi. And we found out earlier, 20,000 hertz and 50 hertz. And K naught then would be when this term is, let's see, yeah, we'd have the S squared as the leading term, S as the following term, so it would be the product of these two right here. Since s is the leading term of the polynomial, this would have to be the constant multiplier. Or 40 times 10 to the 6th pi. Okay, I'm going to go ahead and end the video here and pick up with the next one on the next slide.